Welcome to the Finding Your Next Big One Intact, Understanding and Mitigating Diamond Breakage webinar. I am your organizer, Michelle Beacom, Managing Editor of CIM Magazine, and my co-organizer is Ryan Bergen, Editor-in-Chief of CIM Magazine. Our panelists presenting today are Lucy Hunt and Jane Denoxy of Saskatchewan Research Council's Mining and Minerals Division. We thank our attendees for joining us. Now, just a little housekeeping before we get started. To ensure you have optimal audio, make sure that if you are using your computer audio, that the button for computer is selected on your control panel. If you join by phone, make sure the phone button is selected for your audio. If you have any questions during the presentation, type into the question box on your control panel. The questions will be during the Q&A period. Note that we will have some poll questions during the presentation, so pay attention, please. Now, without further ado, we will turn the webinar over to Lucy Hunt and Jane Denoxy. Oh my word.
Thank you very much for joining us. So as it was introduced today, we're going to be talking about diamond damage, breakage in particular, but diamond damage as a whole, and how we can understand it, and then how we might mitigate it in the future. So just a bit of background about the Saskatchewan Research Council. We are a Crown Corporation and a provincial research council, and where other research councils have kind of been decreasing in size, we've actually grown over the past few years. We have clients within Canada as well as across the world, and because being a Saskatchewan company, we do focus a lot on uranium and potash, but obviously diamonds and as well as other commodities such as lithium, base metals, precious metals and rare earth elements. And really we have the expertise to really help you anywhere from grassroots exploration all the way to mine closure. So the Geoanalytical Laboratories Diamond Services Lab is an internationally recognized, secure and reliable micro and macro diamond recovery facility. So we have a caustic fusion set up to recover micro diamonds, as well as a bulk processing plant to recover macro diamonds. And what we pride ourselves in is the fact that we're at the forefront of developing and applying innovative solutions in diamond exploration. So we are constantly trying to improve our own processes internally, and we're also looking for external improvements that we may be able to bring on board. So we're always improving and passing that along to our clients. And this is really where the Applied Diamond Services group was established. What we saw was a gap in the market. So we saw that companies are spending a lot of money doing bulk sampling. We're processing it for them. And really all they're getting in the end is a frequency size distribution plot, maybe some diamond characterization, but there was a lot of information, a wealth of information that we could pass on and give them to really add value to what the results they're getting. So we put together a team of research scientists and processing engineers to really look at bridging the gap between research and industry. We brought our backgrounds in academia, research, and the wealth of knowledge and experience that we'd had, and put together what I think is a really great team. So as part of this team, we look at diamond characterization and advanced processing. And a few of the things that we do are nitrogen typing. So we look at the nitrogen aggregation state and content of both macro and micro diamonds down to 106 microns. We do our diamond damage or breakage assessments, some work on grading, some organic luminescence, plant design, mine auditing. So really a wealth of information that we can now give you, rather than just a description of the diamonds you might see and the size and amount of those diamonds. Sorry. So now just a brief outline on the presentation we're about to give. So we'll have an introduction on exactly what diamond damage breakage is, why you might be interested in doing a damage assessment, how we determine diamond damage, whether that's looking for features that show that it's natural breakage or damage or fresh breakage and damage, and then how we might mitigate that damage moving forward, and how understanding your damage really gives you a much better idea of your large diamond population and a better handle on your frequency size distribution. And then at the end, we'll go kind of a brief summary. So now we're just going to do a quick poll question. So I'll pass it back to CIM.
Okay, we're still tabulating votes. I'll just give it another few seconds. And here are the results. Back to you, Lucy.
Thank you. So I can see that some of you have carried out diamond damage assessments, but not everybody. So kind of a slide on why you might be interested in doing a diamond damage survey. When we get a parcel of diamonds, we do characterize and size the diamond parcel for the client. But the problem is, without really understanding breakage, a simple characterization and sizing the diamond population may not give you a complete indication of things such as your grade, your value, your economic potential of a deposit. Because actually damage can have an extremely negative impact on all of these. So if you're in your grassroots exploration, the ability to properly assess a newly discovered deposit can be significantly affected by a lot of breakage, and you may not really understand the frequency size distribution of your kimberlite. When it comes to the economics of an existing mine, if you get a lot of damage, then you may be not getting the correct grade that you are predicting. So you're maybe breaking some of your larger diamonds. So your economics are going to be off. So a damage assessment at every stage of every stage of your exploration, from grassroots all the way to a fully functioning mine, could be an important thing to carry out. So there are a number of reasons for diamond damage. Some of these actually can be natural. So one of the ways of which a diamond can naturally be broken is as it's transported to the surface in the kimberlite. If you have a diamond that is heavily included, or for example has a lot of sulfide inclusions, this can really can cause natural breakage. So when you're talking about your diamond that has a sulfide inclusion, it's in the mantle, it is a monosulfide solution. As it's brought to the surface, that monosulfide solution expands. It creates fracturing around the inclusion, and you actually see smearing out of your inclusion along those fractures. So these fractures and damage can just occur internally, but they can also naturally break a diamond. Again, when we're looking at alluvial diamonds, for example, that have been transported, we can see abrasion damage. So there are a number of things that we can look for that show that actually the breakage may have been natural. But again, and this is where it's important to understand breakage, is there are man-made factors that can cause breakage. So during exploration drillage, you may break diamonds. During the extraction process in blasting, again, you may break diamonds, as well as in processing and crushing. And it's particularly in processing, it's here we're really trying to understand damage and breakage and then mitigate it as best we can. So what do we mean by diamond damage? Well, I've already alluded to one of that is breakage, and this is the most severe as it can cause the most loss of revenue. But there are other forms of damage that we look for. So that's impact damage, abrasion damage, and stress. So when we're doing a full damage assessment report, these are the 4 things that we're looking for. So starting with breakage, the first thing to do is we study all the diamonds in the size fractions that we've requested. So we look at the number of diamonds in the parcel and we determine the size frequency distribution of those, and we basically determine which size of diamonds are going to give us the most information. We don't want to waste a company's money looking at the smallest size fractions, so we pick the size fractions that are most relevant. We then look for damage on all of these diamonds, and we assess the breakage. And for this, what we do is we look for surface features that may indicate whether this diamond was freshly broken by man-made forces or was naturally broken. So if a diamond has been naturally broken, you can feel the diamond, even if it's broken almost in the later stages of eruption, it does feel ever so slightly rounded. You can almost close your eyes and you can feel some rounding of the edges. We also see evidence of resorption, so whether that's with trigons, hillocks, some sort of evidence that the diamond was broken and then resorbed ever so slightly. So one of the tools that we have at our disposal at SRC is a scanning electron microscope. And really it just takes great images of diamonds. And here we have 2 secondary electron images of resorbed diamond fragments. So you can see that the diamond on the left has rounding of the edges. So it is a broken diamond, but it was broken within the kimberlite and it has evidence of resorption. The diamond on the right, again, we can see the development of some hillocks, rounding of the edges. So this diamond was broken, but by natural forces, likely by inclusions as the diamond was brought to the surface in the kimberlite. When we're talking about fresh breakage, the features are quite different. Again, if you close your eyes and you feel the diamond, it feels sharp. It feels very, very different. You get conchoidal fractures. If you haven't seen a freshly broken diamond, you may have seen a broken quartz crystal, and they break in the same way. So it's these radiating fracture patterns, usually emanating from an impact point. They're sharp edges, there's no resorption. You get stepped fractures, and there's really a lack of features. So you don't see hillocks, you don't see trigons. So if you see a diamond with this sort of breakage, then we know that it's fresh and likely by man-made forces. And again, here are 2 scanning electron secondary images of a freshly broken diamond. You can see the sharp, non-resorbed edges, the fracture patterns. So this diamond was unfortunately broken by man-made forces. So once we've determined that a diamond has been freshly broken, the next thing is to classify that breakage into a number of categories. And this is done based on the percentage lost. And this gives us therefore an estimate of the unbroken diamond size. This estimate is based on visual inspection, morphology, and really experience, and just looking at thousands and thousands of diamonds. So you can see diamonds go from sort of chips all the way down to small fragments where most of the diamond has been lost. You also may look for multiple fragments of the same stone. So again, you might look for certain features of this diamond, that color, surface features. So when we find one fragment, you start looking in the other parcels, the other size fractions, for other pieces of the diamond that you can start putting it together. And then, as I said, once you've determined this diamond is broken, you determine the estimate percent loss of the diamond, and then you can make an estimate of what that diamond size may have initially been. So on the left is a dodecahedra stone, and it's had some breakage. So it may have measured a 0.7 carat diamond, but once it's reconstituted, it puts the diamond up to 1 carat diamond. The octahedra may have lost a bit more in this example. So you may have analyzed and measured a 1.1 carat diamond, but once you start putting that together with the loss, it could initially have been a 2.1 carat diamond. So you can see how this may start to have an effect on your frequency size distribution. And again, if we find multiple fragments of the same diamond, you're looking at trying to piece these together. So rather than having 3 smaller diamonds, you now have 1 much larger diamond. So again, this affects your frequency size distribution, which Jane will go into further as the presentation continues. So abrasion damage. This is probably the next most common form of damage. It occurs as wear and erosion of your points and your edges in particular. So again, it can be caused by man-made forces. So things such as milling, grinding, scrubbing, or even as you're transporting your kimberlite or your diamonds in the same bag, they can cause wear and damage on the typically edges and points. Again, though, naturally it can occur. So if you have, again, transport of your diamonds in alluvial systems, you're going to get some evidence of damage on your edges and your corners. So if you're doing till sampling, for example, you can look for this sort of damage to determine maybe whether your diamond is close to its source or whether it's traveled some distance from its kimberlite. When we're assessing this damage, again, we're classifying it into different categories based on the amount of damage. And as the damage increases, you go from possibly no revenue loss to revenue loss. And it is important to note, not all abrasion does cause revenue loss. So you may be getting some ever so slight damage of your, say, your points. And this may be just a natural consequence of your processing, and you decide that really it's not important to the overall picture and your overall economics. So these are all things that you can start to determine once you understand your population. The next one is impact damage. So this is typically process induced, and what you look at is on the surface of the diamonds, the presence of marking, scarring, cracking, or any sort of combination of these. It's typically caused by collisions, so whether that's diamond on diamond or diamond on metal. Again, it's classified into a number of categories, and as the categories increase, you get more revenue loss. And this almost goes hand in hand with this next one, which is stress damage. So typically when you have impact damage, you may have evidence of stress. And also with breakage, you'll see maybe impact points with stress. And for those geologists that are watching, if you think of when you look down the thin section at birefringence colors, that's really what we're looking at. We're looking at birefringence patterns, so high order birefringence, or low order if there's less stress. Again, it can be caused by man-made forces, but naturally as well. So as your diamond is brought up to the surface of your kimberlite and your inclusion is expanding, it can create stress internally within the diamond. So you're looking for stress internally that may be natural, but if you're looking on the external outside of the diamond, then this again may be man-made. It's important to note that if you do have a lot of diamonds that are heavily included that have a lot of internal stress because of the inclusions, that can have an impact moving forward when you're cutting your diamonds. These are all other pieces of the puzzle that we can give you. So these are just two images taken from one of our photomicroscopes of two diamond fragments. The one on the left has been naturally broken. You can see the very, very sharp edges. No evidence of resorption, but you can see high birefringence. So again, evidence of impact. The diamond on the right, again is a fragment, but it has evidence of resorption. So you can see resorption, rounding of the edges, resorption features. I'm not sure how easily you can see, but there is some evidence of high birefringence or stress internally within the diamond. So we can start to infer that maybe this diamond core was broken naturally by internal inclusions. So as I alluded to, just because a diamond shows breakage doesn't mean that's the only damage that had occurred. Often breakage goes hand in hand with impact and stress, and again there may be some abrasion. So when we're doing a full damage assessment, we're really looking at all four different types of damage. We also look at factors that may increase diamond damage. So for example, morphology plays a role. If you're lucky enough to have a kimberlite that has beautiful octahedral diamonds, that's great in terms of economics, but they are slightly easier to break than a rounded dodecahedra, just because of the nature of the points and the edges. So again, when we're doing a diamond assessment, we're looking at the type of diamonds that are broken. If it's just the octahedras, that's a certain amount of force. If you're breaking your rounded dodecs as well, then maybe there's a lot more force there that is breaking these diamonds. And as we alluded to, internal things such as inclusions can create stresses that make a diamond more likely to be broken. So again, if we have a parcel of diamonds and what we're seeing is only the heavily included diamonds are showing man-made natural breakage, well, maybe economically speaking, these diamonds were just industrial anyway. So although they are being broken, there may be pre-existing weaknesses that are being exploited. So, okay, we're getting diamond damage, but it's only if our nice gem quality diamonds are being broken that we may start to really worry. So these are all factors that really can be brought into a diamond damage assessment. So it's not just looking at breakage or damage. So this is a secondary electron image again of a broken diamond. We can see some evidence of resorption, and we can see a really nice inclusion cavity on the surface. So here we can again see a reason why this diamond broke. There's nothing we could do about it. There's nothing we can do to stop this sort of breakage. It's just a natural factor, a natural consequence of having an included diamond. So really, when we do a breakage analysis report, there's a lot of different things that we can bring into it. So if we can get any information on the type of kimberlite, the lithology of the kimberlite, if you have a very competent, hard kimberlite that's being processed, you're obviously going to have to apply a lot more force to break your kimberlite to extract your diamonds. You're breaking your kimberlite, so the chances of breaking a diamond therefore may increase. Again, your diamond morphology may play a part. If you have a large population of diamonds that you're expecting to see, you may have to change how you process that kimberlite to stop breakage. Again, if you have a lot of inclusions, the number of inclusions, the kimberlite morphology may change with depth, with drill hole depth. So we can look at whether we see different changes in breakage patterns and the amount of breakage as we go down in the drill hole. And then look at whether any of our plant processing operating parameters have changed and whether that may have affected our diamond breakage or damage. And what we're hoping to, again, we're always trying to strive to improve and give our clients as much information as we can, is provide an estimate of potential revenue loss. So we're constantly going on courses, increasing our knowledge base, and we're working with some more experts in the field to provide a possible dollar amount, a dollar value on what you've really lost in terms of breakage. So this is what we're at moving forward. So now I'm going to pass over to Jane, and also there'll be another poll question right now for you to get your teeth into. Okay, thank you.
I don't know which button I'm meant to press.
I'm just collecting responses. Okay. Here are the results. And now I will pass it over to Jane.
Good day. Now we're looking at the reasons for fresh breakages that will occur in your processing plant. There are a number of reasons. The first and foremost is you're using possibly the incorrect comminution technology. Then we're also going to discuss a little bit of sizing your equipment. Have you got the right size on your equipment? The incorrect selection of pumps. Some high energy ejectors, they can also be causing problem in your plant, and then also some of your internal stresses within the diamonds and how that impacts your plant design. Starting with comminution, we all know that diamond is the hardest mineral on our planet, and one of the ways that geologists used to test for diamonds, or people used to test for diamonds, is to test its hardness, and they used to hit it with a hammer. So you can see previously that a number of diamonds did get broken by using a test with a hammer, saying that if it broke, then it wasn't a diamond. But diamond is brittle, and if you do hit it with a hammer, I assure you it will shatter into millions of pieces. So what we're looking at is comminution technology that is diamond friendly. So you wouldn't want to use a azimuth crusher, or even your rod mills and your ball mills can be very diamond unfriendly. What has taken popularity at the moment is your autogenous mills. When they are run at a lower speed, then you will find that they can actually commute your kimberlite quite in a diamond friendly manner, but you also need to have the right fill in the mill so that your material that is cascading is falling onto your slurry and not impacting on the size of a mill. The other very diamond friendly comminution technology is your high pressure roll crushers, which actually just use compressional forces to liberate your diamonds and to break up your kimberlite. Looking at sizing of your equipment, we all understand that if you have a 5 millimeter rock and you push it through a 3 millimeter hole, it is going to break. So, and I have heard a number of stories that DMS actually breaks diamonds, but the DMS only breaks diamonds, or diamond breakage only occurs around DMS circuits when the equipment is not sized correctly for that size diamonds. So if you're putting the wrong size stream through that cyclone and you have it holding the wrong size diamond in that stream, then yes, that diamond will be broken. So it is very important to actually know your size frequency distributions of your diamonds in your deposit so that you can select the right equipment for processing your diamonds. And that also applies to pipes. Your pipes should be, the aperture of your pipe should be at least 3 times the size of the largest particle that is being passed through it. Bearing in mind that pipes and cyclones, you have no degrees of freedom. Your material moves in one direction, and then your X and Y, which is orthogonal to your direction of flow, you have very little degrees of movement. So you have to get to making sure that your pipes and your cyclones are sized correctly for the size of material that it is designated to process on that various streams in your plant. Let's look at pumps. Pumps have also received a bit of a poor reputation for breaking diamonds. But again, if your diamonds have been, if you know your diamond size and your pumps can accommodate that diamond size. If you look at the configuration of your impellers, if your diamonds can fit within those impellers, then you should be okay with that pump processing those diamonds. If your material is in a slurry, your slurry is moving fast. So one of the arguments has been your impeller speed, but your material is already moving fast. So your relative speed of your slurry to your impellers shouldn't be too much of an issue. Then the material coatings of your pumps, as soon as you put in wear coatings, that can also absorb some of the impacts that could occur between the impellers and the diamonds, and all of those things help with preserving the diamonds in their wholeness and not actually causing damage to the diamonds. So if you know, I am emphasizing again, know your diamond size frequency distribution, and then you can size your equipment used on your processing plant, and you should not incur diamond damage. Another problem that I have seen recently is ejectors. You can get different size ejectors for your different size streams. The objective of the ejectors is just to displace your material moving from your mainstream over your splitter plate. So if you know that how far you've got to move your particle and the size of the particle, you can actually size your ejectors, calculate the force required in the air to move it over, and then ensure that you actually just do the displacement of your particles from that mainstream. Then regarding the housing, you do not want to hit the various size of your bins. So you would want it to fall, say, more on a kimberlite, on a softer material. So looking at your housing, you could do lamination of the housing, and even your splitter plate, you could use a polymer splitter plate so that your diamonds don't keep hitting onto some hard material and getting impact damage. And lastly, yes, there is internal stress in some of the diamonds. Lucy has actually explained how you can identify it, and you can see there with the birefringins. But when you do see those kind of diamonds in your population, then you have to be even more careful with how you're handling the forces and the impacts in your plant. Minimize the amount of impacts that you have. And then you can also look at the source of the stress. Are they occurring around inclusions that are actually going to be polished off? So are they going to be detrimental to your diamond if they do break along those inclusion areas, or will you be able to preserve the value of that stone? So mitigating fresh breakages. There's a number of steps that you can take. First of all, like I've emphasized, understand your diamond size frequency distribution, and with that information, then select what streams you're going to set up in your process plant, and then select the correct equipment for each stream. Use diamond-friendly equipment, so don't use combination technologies that's going to provide high impact and high forces on your diamonds. Well, you can have compressional forces, but not impact forces. Then the other aspect is your fall distances of your diamonds onto hard surfaces. A study has been conducted where diamonds have been allowed to drop from different heights, and they found that even at a distance of 10 centimeters, impact damage has been seen on a diamond surfaces, on the points of diamonds. So really keep your free fall distances to a minimum. And last but not least, diamond on diamond contact. Try and reduce any diamond on diamond occurrences, especially when you get to the high concentration areas in your plant. And then when you come to transportation, be very careful how you actually package your diamonds into packages because abrasion will occur. Now we're getting on to looking at your size frequency distribution. This is an important study to conduct if you want to understand what size diamonds you will have in your deposit and actually to preserve those sizes. So what I've got here on the screen is a graph of your macro and micro diamonds recovered from your exploration and your bulk sampling exercises, and they are depicted by the green round dots on the screen. And what I've done then is taken the population and plotted on a log-log curve, where is the cumulative number of diamonds occurring against the size of the diamond. A paper has been written on this. If you do want a copy of the paper, please just contact me. And what we've shown in the paper is how the log normal distribution of the diamonds can be plotted very accurately, 99.9% accuracy to a quadratic curve in this manner. But anyway, regarding the diamonds and their distribution, once it's plotted here, you can then quite accurately extrapolate it, as what I've done here with the blue squares, into the regions where you haven't explored. So if you've just got a small sample, you can take that sample of kimberlite and extrapolate it for the entire kimberlite facet that you are expecting. And once you've done it for the entire kimberlite facet, you can start looking at what are your larger diamonds that you could occur in that kimberlite facet. So you can see a slight movement between the previous slide and this slide. I'm just going to go back. That's the previous slide. That's just looking at the diamonds as they came out of your exploration sample. Moving on to the next curve. This one curve is now corrected for breakages. So once you've done the diamond breakage study, and you can now modify what diamonds were broken and enhance those the sizes of the diamonds, you will find that that curve will move slightly upwards and to the right, indicating that now when you extrapolate to your entire kimberlite facet, a slightly larger diamond size population could be expected in your kimberlite facet. Now, I just want to emphasize this study needs to be done for each kimberlite facet because each kimberlite facet pulse usually has a different diamond population. Here's a table that's been now extracted from the graphs that you've just seen. So what I've got here on the far right is for the whole kimberlite facet. So you can see in this column here with just the black writing, that is the number of large diamonds, everything plus 10 millimeters, that you could expect from that kimberlite facet without the diamond breakage study. Now, when you do the diamond breakage study, those diamond numbers have been corrected, as you see in red, and they have increased slightly. Now, this kimberlite facet was expected to take 4 years to mine it completely. So if you just look at saying, yes, that a 45 millimeter diamond is quite a big size diamond to design your plant around, and that there is some risk because there is some probability associated with it, you might want to look at what's the largest diamond that could occur per month. And then you can see here, these two columns are the sizes of diamonds that you would expect per month. The black numbers are for when it hasn't been corrected, that's just from what you've achieved out of your kimberlite facet from your exploration data, and the red is after your breakage study. And you can see here, each month you could expect a 40 millimeter diamond and possibly 2 35 millimeter diamonds. But you could say, well, even this is a little bit risky, and you could do the same study for every 12 months. And then you might say, yes, that your top size then is a 30 millimeter diamond, and then be prepared to break, say, 3 diamonds on an annual basis. So all of these play into the economics of your deposit and also what the stress is on the diamonds, so saying what are the chances are of the larger diamonds being your gem and nice quality, high value stones. So looking at all the breakages and how you actually use the information to mitigate diamond breakages in the plant, I hope that you can understand that from the conclusions that you've now looked at, you can how to actually identify your natural and your fresh breakages. Your naturals breakages you can't do much about, but your fresh breakages, I've given you some tools where you can mitigate that moving forward. Very important from this webinar is that you do need to look at your size frequency distribution, because it gives you a lot of information on how your process is performing around your large diamonds. Equipment can be made friendly with the use of polymers, either lining boxes and bins with latex or polymer knife gate splitters, those kind of things where any impact on the diamond can be absorbed by the polymers. Really try and minimize the distance where your diamonds are falling onto hard surfaces, because that will reduce the impacts within your plant. And last but not least, diamond on diamond contact. I have seen plenty of diamond damage and abrasive forces on the diamond surfaces because there has been diamond and diamond interaction. Be aware that in drills, whether you're going to the dentist or even in exploration, they've all got diamond bits because of the abrasive nature of the diamonds. So they are highly abrasive where they are in contact with one another. And that concludes the aspects of the webinar that we wanted to relay to you. Over to any questions.
Thank you, Jane and Lucy. Just a reminder for anyone with questions, you'll notice in the control panel on the right-hand side, or it may not be on the right-hand side, but in the control panel, there is a space for asking questions. Please enter them in there. So I do have a few questions here. One, how do you determine where in the process plant the breakage is occurring? It seems that the end result is a cumulative effect of many breakage events.
There's a few things you can look at when you're just studying the diamond. So if you see, for example, you're just getting, say, one fragment of a diamond, and when you look in the smaller populations, you're not really seeing any larger fragments. You're just maybe seeing very, very small, tiny diamonds, and maybe even powder at this point. I mean, the forces that have broken that diamond are a lot more than if you're kind of fracturing diamonds a little bit and getting a lot of bigger fragments. If you're getting a lot of impact damage, a lot of point damage, then again, that implies different stresses, different forces. So you can look at how the diamond has been damaged to give some inferences on what may have damaged the diamond. And then obviously I'm then talking with processing engineers, experts like Jane, to look at how the plant is operating, how it's run, and where the most likely places that this diamond has been damaged.
And I'm going to add to that, like my previous webinar on audits, taking samples around each process, and then you will identify exactly which process is causing what damage and by how much. So audits are very important, and then also, like Lucy was saying, the study of how it's broken will give you an indication on what exactly in the equipment is causing the damage and what you need to modify to reduce those occurrences.
Great, thank you. Yeah, and we should also note that that previous webinar is on audits is available on the CIM magazine site for you to check out with the audio and so on. All right, another question. What about, someone asked, what about very short ag mills so that the number of breakage events before exiting the mill is quite low? Is that clear to you?
No, okay, no, sorry. No, can you just repeat that question, please? Sorry.
Yeah, the person's asking about very short autogenous grinding mills. So that the number of breakage events before exiting the mill is quite low. This may be about equipment selection.
Yes. Okay. So with any mill, what you want to do is make sure you've got enough fill so that when you have got your cataracting occurrences, they are not being picked up and hit against the side of the mill. You actually want it to try and fall in the slurry. I have done some tests with combination tracers to actually look at the aspects to minimize diamond breakage, and we were fine up until a certain critical speed, but each mill is to its own. So you've got to do the assessment on each individual mill, but you can do test work around your mill to actually assess what kind of operating parameters to minimize your diamond breakage within your autogenous mill. Yes.
So you can do a diamond damage assessment and really see if before or after changing some of these parameters, whether you are actually getting any damage, and maybe you're not, and then if you are, how you might change some of the plant.
And with combination, there is combination simulants that you can utilize to help you assess what kind of impact forces are occurring in your combination technology.
Okay. And do you have any wisdom about rubber-lined ag mills versus steel?
Well, if there are steel, you don't want your material to be falling onto the edge of the mills. You actually want it cataracting and falling down onto your actual slurry before it actually hits the side of the mill. So, and that's all a function of your critical speed. So round about, say, up to 65% of your critical speed and the right fill in your mill, you shouldn't be impacting on the edges of on the sides of the mill. So whether it's rubber lined or steel, it shouldn't make too much of a difference. But I mean, if you do have to push up your speed with some of the harder kimberlites, then yes, I would prefer rubber lined.
Okay. And somebody else asked about the broken diamonds that you showed throughout your presentation. For those that you showed, were they sampled at various locations in a process or just at the output?
It varies a lot. It really, we get clients coming with samples from early exploration to, yes, when they are in a full mine production and they want to assess whether they are getting any diamond breakage. So they're kind of pictures from throughout production and exploration.
But they're more generally, after they've been through the process. Most of them. We can study diamonds from audits, but we're waiting for people to send us more samples from audits to assess where the breakages occur in those different processes. But in this presentation, it was more at the end result, either of exploration or a process.
And I mean, really, when you're doing a diamond damage assessment of an exploration sample, obviously understanding damage is important, but at that point, you're not necessarily trying to mitigate it, you're trying to understand it moving forward. So whereas when you're in a fully operating plant, you're then really looking at trying to mitigate your damage. So you get slightly different conclusions or outcomes at the end of it. Obviously the assessment is the same, but exactly what you're trying to get out of it is slightly different.
Okay, somebody asked you to comment on optical sorting. Is XRD technology pretty much a standard in process plants now?
XRT is becoming very popular, but I wouldn't say it's actually a standard yet. It's very popular for the recovery of the larger stones. I think there's still quite a bit of maturity to occur on that technology.
Okay. And then someone asked, what is your experience with ceramic simulants to characterize breakage? Do you think this is a reliable method? Any tips and hints to interpret the data?
I've used the ceramic simulants to evaluate combination technologies, but it's an indication that the ceramic simulants are not as hard as the diamond. So if you are getting chips on the simulants, you might get a little bit of impact on the diamonds. But but if you're getting your simulants totally preserved, then it's a worst case for your diamond. So it would simulate, say, more of an included, a more weakened diamond. But yes, it's the way to go because you can do lots of simulants compared to like your 1 or 2 diamonds. So it's nice to run repeated tests with your simulants.
Okay, thank you. So I just I've got another question here. Just not, the display is not cooperating. So I'll do my best here to read it for you. I've been involved in mine sizing, run of mine pre-mill. In this case, underground, preliminary rock breaker, grizzly, less than 1 meter. So this would.
That sounds very horrible.
It's written in shorthand here, and I'm having trouble seeing the question in its entirety. Are you aware, or have you defined a better ore reducing process than, I guess, the breaker / grizzly, and then secondary roll sizer down to, I think the first one was down to 1 meter or sub 1 meter, and then the roll sizer sub 300 millimeters.
Okay, so this is in exploration, definitely exploration. This isn't for your macros. And yes, you're going to get a lot of breakages with those technologies. I have mainly concentrated on the macros. The micros is once you actually recovered your micro diamonds, then usually gets handed over to Lucy for the breakage study and those kind of things. I haven't been too much involved in going out for exploration exercises, but I think that's something that needs to be looked at in the future, whether there should be a bit more preservation on the combination technologies used in the exploration exercises.
Yeah, I mean, again, when we are talking about exploration, okay, it's not great to break your diamonds, but at least if you can understand the diamonds, and okay, you may have found a 5-carat diamond. It is now in 2, 1, and 0.5 pieces. If you can understand your breakage and put those together, you can then go forward with a 5-carat diamond. So trying to mitigate breakage in exploration is important. It's not necessarily our skill set right now, but if you can at least understand how your diamonds have been broken, you can at least take sort of an unbroken parcel of diamonds forward for future exploration, for economics, determining whether kimberlite is prospective moving ahead.
And the other aspect is we also have caustic fusion. So sometimes what clients will do is they will take a larger core sample and you put it into caustic fusion, and that just like dissolves all the kimberlite and then preserves your diamonds. So the diamonds that are locked up in the core samples that go into caustic fusion do not get damaged.
No.
So if you can do more work in the caustic fusion line, then you can actually get a better representation of your size frequency distributions from your micros.
Yeah.
Okay.
If that helps.
Yeah.
So someone asked on one of the first slides that you showed, there was an image of small rings on the surface of the diamond. Do you have any idea what is the cause of those features?
So it's birefringence, so it's stress. So man-made reasons, if you have an impact, so diamond on diamond, diamond on metal, you may get something like fracturing or cracking. You may just get stress. So it's just an indication that you've had some damage that may not have caused physical damage like a fracture or a crack. If you're talking about the same sort of high birefringence colors, the kind of the pinks, the oranges, these radiating color patterns internally, then this is due to inclusions usually. So your inclusions expanded, and again, it's created stress within the diamond. If it's just on the surface and you haven't created fracturing associated with it, I mean, it's evidence that your diamonds have had impact damage, but it's not necessarily bad in terms of economics. The chances are this part of the diamond is going to get cut off, and if it's not going too deeply into your diamond, it's probably not going to affect cutting and polishing. If you have a lot of internal stress actually related to inclusions that really we can't do anything about, these can have significant impacts when you are cutting and polishing your diamond. So it's sort of internally or externally related to impacts and stresses on the diamond.
Okay. So someone had a follow-up question about around the ag mill. So if the ag mill is not installed, is the diamond breakage with tracers adequate to anticipate diamond breakage? In other words, do we have test work before the mill sizing and after the fact in operation results? Do they align?
Okay, I'm just trying to understand the question a little bit. So you're saying, okay, so you're moving from your bulk sampling to your designing for your process plant, and you just want to make sure that the design that you've chosen for your ag mill is correct. So you can do, like I said, the simulant testing, and just to make sure that what were your operating parameters, so you can do a number of simulations along those lines. And you can use simulants for that. And if you do incur a little bit of damage on your simulants, that's fine. But you just want to make sure that you're not breaking the simulants. If you start breaking the simulants, then you know that is how you've set up, how you're going to be running your ag mill in your main plant is going to be problematic. But yes, you can go a long way with actually simulating your throughput, your water usage, your fill on your plant, your residence time on your AG mill, and putting the simulants in and making sure that those parameters are correct for when you go into production. I think that's what you're asking.
Okay, and of course, I think these questions can be followed up on.
Yes, you can follow up on the questions. Yes, please do. Yes.
Okay.
I have done something similar to that on ag mill testing. So yes, that is the way I recommend to go.
Okay, and I get so someone asked if you mentioned simulants for comminution. Are they available for the general public or only De Beers sites? And
yeah, I thought that I purchased them off the De Beers site. You're right, good question. I thought they were for the general public. I'd assumed they were for the general public. But they're on the De Beers sites. And then there are crash comminution simulants to represent diamond, in the circuit.
okay.
Yeah. De Beers, you've got some business.
So someone asked if you have an opinion on microwave-assisted rock breakage as it relates to diamond damage. Intuitively, this will reduce the energy required for liberation, but the question asker is curious as to whether there's some other unforeseen risk to the diamonds due to the microwaves.
I don't have an opinion on that at the moment.
Yeah, I mean, if you have a diamond that's not included and doesn't have any pre-existing weaknesses, I can't see the microwaves would damage the diamond. Again,
it's like passing a light beam. Microwave is electromagnetic wave, so you can put a light wave through a diamond, a longer wavelength. Who cares?
Yeah.
Okay.
I mean, with anything, if there are pre-existing weaknesses, then anything may create more breakage.
I'll be more concerned with an acoustic wave if there are inclusions.
Yeah. But yeah.
But electromagnetic waves, I just see it just the longer end of the spectrum.
Yeah.
Okay. So again, about ag mills, if you have an ag mill already installed, is there an optimum slurry density that helps reduce breakage?
That I haven't tested. It usually can get quite thick in an ag mill. It's something we can keep an eye on moving forward.
Yeah, I mean, if it's just something that we're interested in, we're always looking to try new tests and to set up new circuits if it's required.
If that's a concern, yes, yes.
Okay. And someone asked if you've done any studies to compare diamond damage from conventional blasting versus non-blasting mining methods, such as the use of mechanical mining machines, such as a surface miner that uses hardened teeth or picks.
We haven't. I mean, if it's more just the samples haven't been sent to us, but if someone was interested in this, if moving forward, then obviously we'd be more than happy to kind of get on board and test things like this.
Evaluate, yeah.
Yeah.
Just taking samples and looking, comparing their breakages, yeah. No, we haven't, yeah. But I'm going to say that'd be an easy test, you know, like taking a sample, we could do some in diffusion and some, and looking, making a comparative study, easy.
Okay. So just we'll run down here, see what else we have. Well, so I think that that concludes. I think there may be some questions here that might bear some following up on from those who have asked, and I don't want to cut it short. I just want to make sure that we can get the question addressed as comprehensively and clearly as possible. So I think you two are both available for that.
Yes.
Okay.
Yes.
All right, so thank you to all of you who asked those questions, and we want to make sure that we get comprehensive answers for you.
Thank you.
All right, so I will pass that now, I guess, over to you, Michelle. Thank you.
Well, thank you, Lucy and Jane, for this excellent webinar. We've really learned a lot. I'd like to thank all our attendees for joining us. And also a little housekeeping. Please fill out the short survey that pops up on your screen at the end of the webinar, if you could, please. A link to the video recording of this webinar will be sent to you in an email this afternoon. As well, the video will be available on the CIM magazine, that's magazine.cim.org, in the Diamond Webinar Series link. There's a picture on the homepage, and also on the Saskatchewan Research Council website. Thanks again for joining us today, and we hope to see you all at the third webinar in the Diamond series, using Diamond typing to improve recovery techniques, on September 24th, 2019 at noon Eastern Daylight Savings Time. Registration is already open, and a link to register will be in the follow-up email you receive this afternoon. Thank you very much for joining us for the Diamond Webinar Series again.
Thank you.
Thank you. And sorry, just one last about if people just want access to the PowerPoint itself, I assume they can reach out to you, Lucy or Jane.
Okay. Yes.
Yeah.
Yes. Yeah.
Okay.
Either of us. Yeah. Our contact details, what's on the screen. Either of us, we can give you their PowerPoint presentation. Yeah.
Wonderful. Thank you.
Thank you
Thank
very
you.
much.
Thanks. Okay.
And bye.
Bye.